take some notes. Okay, it's going to be sort of a jumble of minor pieces of information, and hopefully it'll sort of bring things together for us. Let's just kind of recap lives for the past week or so. We've talked about work, and we've talked about energy and energy conservation. We've talked about springs and how elastic things work, and then we've talked about when mechanical energy is not conserved, which is the case of the bouncy ball, right? Mechanical energy was not conserved. Mechanical energy is mental and kinetic. So whatever the form of energy that was dissipated into the ground when the bouncy ball lost some of its energy, it definitely was not mechanical because it didn't come back into the system. Okay, it was taken out of the system by whatever which was doing work on the ball. So that's kind of where we are at this point. If we think about work, there are some other concepts that come into play, and one of them is called power. If I ask you how power is acquired, think about it like in your life. How do you gain power? What do you do? Okay. And how do you take it from other people? What does it take? It takes work and time. Okay, so if you want to gain power, you have to work hard over some time. And that is the equation for power. Work over time. Power is defined as the rate at which work is done. The rate at which work is done. So, can somebody tell me the units of power? Joules per second. Yes, joules per second. And the way you figured that out was the units of work, which are joules, divided by the units of time, which are seconds. So the units of power are joules per second. And that has its own special name. Does anybody know? Named after a Scottish physicist who developed the steam engine. No? That didn't help? Watt. It's a watt. And for watt, we use the letter W, which I know is really unfortunate because also in the equation we use the letter W, but they're different things. Right? This represents work in an equation. This goes after a number. Like there are. Yep, exactly. So power is what we measure things like light bulbs in. Right? What's the power output of like a standard light bulb? 60 to 120 watts, somewhere in there, right? So when you look at a light bulb, that number, that's the power output of that, the energy per second that is putting out. So one light bulb is equal to approximately 100 watts. Does anybody know what the power output of the sun is?
A billion, trillion, million.
Something like that. What do you say, like a trillion, million, 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 or something like that? 4 times 10 to the 26 watts. I think. Well, we can measure the amount of power that we receive, and we can measure how much it's dissipated from the sun. So, for example, here in Tucson, every day, approximately, in 1 square meter of the earth, we receive about 1,000 watts. That's not an actual square meter, but in a square meter, each square meter receives about 1,000 watts. Okay, and that's on if you look at the Earth, if you look at the sun, the surface of the sun is outputting a certain amount of power. And that power is distributed evenly over the surface of the sun. But we're not there, right? We're over here somewhere. And so now that power is distributed evenly over the surface of this sphere. And so it's gone from this amount to this amount. And we can figure out how much the power has been spread out from here to here by measuring the power here at the surface of the Earth and then extrapolating back to the surface of the sun. It's not super straightforward, but it's also not super complicated, right? If you imagine that like the Earth is on this imaginary giant sphere, all of the sun's power is distributed evenly over this giant sphere because it all goes equally in all directions. We can kind of imagine all of that shrunk back down to coming from here, which has the radius of the sun, and figure out how much power we have. So 4.7 per second. That's joules per second. Yep. So every second. Well, but it's true. But we talked about what happens in the core of the sun, right? Big stuff, big doings, right? We have the E equals mc squared thing happening in there. A lot of energy is output, right? Every time there's a fusion reaction, a lot of energy comes out. Okay. Anyway, so power. That's power. So here's a question for you. Let's say who in here is a runner? Have you ever run Sabina Canyon?
Yeah.
So you and I are racing. Okay, we're going up Sabina Canyon, and we're going up the last 3/4 of a mile at Sabina Canyon. So this is an exaggeration. It's really like this, right? It's like you're climbing up the hill. Okay. So this is 3/4 of a mile, and I think that the rise is like 400 feet. Anyway, very difficult, really annoying, and we're racing. Okay, and obviously I win because I'm an elite athlete. So when we get to the top, so it takes me 4 minutes to go the last 3/4 of a mile, and it takes Nathan like 8 minutes. In reality, I'm pretty sure it takes me like 10 minutes. So let's just assume for this purpose that we have the same mass. Okay? If I ask you which one of the two of us did in getting to the top of this hill, what would you say? Yes. That is good. Why do you say the same? Because all the other ones had already been guessed, right? Yeah. That's okay. That's fine. I mean, at some point you can like read my face, right? Oh, that must be the right answer. Yeah, it is the right answer. The same amount of work. Because if we have the same mass, we have to do the same amount of work against gravity to raise ourselves to a certain height. Okay, work is the amount of energy. I have to put energy into my system to increase my potential energy, right? I'm going from here to here. The amount of increase of my potential energy is the amount of energy that I have to put into the system. And since we have the same mass, the amount of energy I have to put into my system is the same amount of energy that he has to put into his system, right? We're both raising 400 feet. The amount of time it takes has nothing to do with the amount of work done. Yes? Is that only true to get mass? So now, next question, which one of us has a larger power output? How do you know that? Yeah, time is in the denominator. My time is smaller, therefore my power output is bigger. Okay? Does that make sense? We did the same amount of work. I did it faster, therefore my power output is higher. Double. Okay. So that's power. Do you have any questions about power? Sorry. The next about is the relationship between work and kinetic energy. What do you mean by any time soon before things are going crazy? I think I have your test scheduled the day before Thanksgiving. That was the reasoning, because otherwise it's like the Monday when you come back, which is just terrible, right? Just get it over with. But we'll see how things go. Next, so it would be like, yeah, I know. That's why we need to have the test, because it's like, yeah. So it's either the Tuesday before break or the Monday before break. Those are really the two options. So right now it's on the calendar, which you can all look at on my website. It's on the calendar as Tuesday. Okay. Oh, the relationship and kinetic energy. It's called the work kinetic energy theorem. Because physicists are so clever that we could come up with this name. Work kinetic energy theorem defines the relationship between the net work done on something and the changing kinetic energy of that system. So if we just think back for a second, I know it's been a while since we talked about work, but the equation for work is equal to the force times the displacement times cosine of the angle between the force and the displacement. Right? I'm sorry, did we use the letter D? I think we used the letter D. So it's the force times the displacement times the angle between those two. And it's horizontal. It's any displacement. Okay? The cosine theta takes care of all of the weird stuff that you have to think about. But the point is that the work done by a force is only done by the component of the force that's in the same direction as the displacement. Like, if you have a net force, if you have a net work done, right? If I want to know what is the net work done, then I just replace the force with net force, right? If there is a net work that's not zero, that means there's a net force that's not zero. And if the net force is not zero, that means there is an acceleration. Okay, I'm gonna go through that process one more time. If this number, net work, is not zero, that means that the net force is not zero. If the net force acting on something is not zero, then your acceleration is not zero. Okay? And what that implies is that your acceleration is causing a change in velocity. That's the definition of acceleration, right? If you have a change in velocity, then you have a change in kinetic energy. If you have a not zero acceleration, remember acceleration is equal to delta V over T. If you have a not zero acceleration, that means that your velocity has to be changing. And if that's true, then your kinetic energy has to be changing. Right? So this not zero means this not zero means this not zero means this not zero. So if there's a net work. All right, but once I write down the actual relationship, it will be very apparent, or not apparent, but easy, I guess. And the relationship is that the net work done on a system is equal to the change in kinetic energy. This is the work kinetic energy theorem, and it comes into play a lot. And it's actually not really a new thing, right? If I said, like when we did force problems, in fact, remember on your test when it was the guy who was sliding into one of the bases, right? And you had to, if you did it correctly, you had to first sum the forces and find the acceleration and then use kinematics to find the distance that he traveled or something. You could use the work kinetic energy theorem to do that as well. It's basically taking all of that stuff and putting it into one equation, where the net work is the force times the distance times the cosine of theta, and the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. Right? Change in kinetic energy, when you have a delta like this, it's kinetic energy final minus kinetic energy initial. Right? That's what delta means. So if I'm slowing down, then my final kinetic energy is smaller than my initial, and this number becomes negative, which means negative work is done on the system. It's absolutely, that's a situation where the guy who's sliding into the base, right? He starts out with some velocity and then moves to rest. Friction has done negative work on him by taking energy out of the system. That energy that's been taken out is what's causing the change in the kinetic energy. Right? What's happening to his potential energy is nothing is happening to his potential energy. He's sliding across some sort of uniform horizontal surface. It's not changing. Whatever it was to start with is the same as what it is to end with. So we can just say it's 0 in both cases. Okay, so the net work done on something is equal to 2. That's the work done. You guys have questions? Well, so what I have for you, and I feel like you're going to be prepared for most of this. What I have for you is a packet, and it seems like a lot of pages, but a lot of it is like multiple choice or like one-word answers. Okay, like there aren't any calculations at all on the first page, even though it looks like it's all stuff. Okay. So I want you to do this packet for a moment. There's something, well, I guess a lot of it is asking you to deal with what we call energy bar graphs, which are designed to help you conceptually understand what happens to energy in a system as we go from one form to another. So, for example, if we think about the work kinetic energy here, we think about the guy who's sliding into third base, okay? He's sliding into third base, and every energy bar graph is going to give you like something that looks like this: PE, KE, and then work done by external forces. Work done by external forces is like friction or applied force or somebody who's like doing something or taking mechanical energy in or out of the system. Okay, and then it gives you some sort of 0 level like this, and it's like a little bar graph, and this is like initial, and then there's another one. Just bear with me for 1 second, and kinetic energy, and then that's it. And this is fine. So, for example, when you've got a guy who's running across the ground, right, and he's about to slide, so he's just starting to slide. He's got a lot of kinetic energy, right? So let's just say in my bar graph that his kinetic energy is as much as it can be. Okay, positive. This is negative. This is positive. And then there's no potential energy, right? He's on the ground. And then when he reaches the base, he's not moving anymore, right? The question or whatever, the point is that he's come to rest when he's slid into the base. So he has no kinetic energy and no potential energy, right? Which means the total net energy of him at this point is 0. How did it go from kinetic energy in whatever number it is to being 0? The work done by external forces, in this case friction, has been negative of whatever the kinetic energy was. Okay, so it's like an analysis of the situation. It's like, here's a better way for me to explain it. I'm going to hand out this packet to you, and then we're going to do one together. Because I think that I can really do that now. So let's look at number the very first, on the back of the very first page, the bottom where it says number 1, the numbers are going to be all over the place, but where it says number 1, you've got a ball that's falling, initial, final. It shows you the initial position and the final position. And they're asking you to fill out this little bar graph thing, okay? So the idea is that the initial kinetic energy plus the initial potential energy plus whatever work is done by external forces equals the final kinetic plus the final potential. So initially, what type of energy does the system have?
Potential.
Potential. It's all potential. Not potential energy, but I would, just because it makes the most sense to make it as positive as possible. So what you would do is you would fill in the potential all the way to the top. Or to whatever number, it doesn't really matter. This is a qualitative analysis. And then, initially there isn't any kinetic energy, okay? And it says there is no air resistance, which means there is no work done, very good, by external forces or anything. There's nothing else that could do work. Air resistance would give you negative work, yep. And then finally, right before it hits the ground, what has happened to the potential energy? Yeah, the potential has gone to zero, therefore the kinetic now has to be at whatever level the potential was to start with, right? So if you didn't fill the potential up all the way, then you can't fill the kinetic up all the way, right? It didn't gain energy from anywhere. There was no positive work done. Does that make sense a little bit? Now let me just find you one that's a little bit more difficult. That way you can, you'll have an example of both. I guess on the next page, number 3. It says a skier starts from rest on top of hill A and skis into the valley and back up onto hill B. The skier utilizes her poles to propel herself across the snow, thus doing work to change her total mechanical energy. The initial state is on top of hill A and the final state is on top of hill B. Okay, so let's start at the beginning. It says, a skier starts from rest on top of hill A. Snow. So, well, start from rest tells you that there's no kinetic, right? For sure there's no kinetic. But we can't start out with full potential because then it says she adds work to the system. She does work on herself to propel herself. So if we maximize the potential, then we can't go anywhere with that. If you start out somewhere, it doesn't matter, right? This is your qualitative analysis. So you just pick some level, right? You start with some number that has to do with your potential energy. Now let's forget about the work for a second. But we know that at the top of hill B, what has happened to the potential energy? It's decreased, right? We don't know exactly how much it's decreased, but it's definitely less than it was, right? So you can pick some level that's lower. Because it's still on top of a hill. You could have actually chosen to make hill B like 0 height, but I want to make it a little bit more apparent that we're still like up from 0 level. And then it says that she does work to change her total mechanical energy. But it says she utilizes her poles to propel herself. So she's doing positive work upon herself. She's not pulling herself down, right? She's not like pizza-ing. She's putting energy into the system. So that means whatever the work that's done is some number and it's positive, right? That's why I left a little space here to leave room for some work done without having to like max out or go above the bar graph.
Do those two have to like make a whole, like potential energy plus the work done? Like, is that
I would just to make it easier on myself. Yeah. Because that way over here, instead of saying, I don't know how much kinetic energy to put, I would say that the total, so the point of this, I'm doing a horrible job, but the point of this is that the total amount of energy on this side, so if you do whatever you have to do to make this equal like one whole bar, then over here, whatever potential there is, plus whatever kinetic there is, has to equal the same total amount of energy. So if I make this equal to one whole bar, which I kind of try to do here, then here I need to put, this much kinetic energy to make it equal one whole bar. Does that kind of Make sense? Okay. Well, I mean, it's something you kind of have to work through a little bit on your own. These questions come from the physics classroom website, so you can always look on the website, although the Wi-Fi in this room does not work right now. But in general, at home, you could look on the website and you could get a little bit more help with these bar graphs. They're supposed to be helpful, and I really do think once you get the hang of them, they will be helpful to give you kind of a sense of what does it mean when energy is put into or taken out of a system, and what does it mean when there is no work done, and how does potential connect to kinetic and all that stuff. And then after that, the last little bit is dealing with different types of conservation of energy and when work is done and when work is not. So all of the answers are in the back of the room. So if you want to, take a picture of them or whatever, you can do that, or you can just check it as you work. You still have 15 minutes left in the class to get going on this and ask whatever questions you have. Okay?